Good morning, everybody. And first of all, I want to thank the organizers for having me here and present part of my work. So, as my title says, I'm going to talk about transition from viscous to inertial regime in dense suspensions. So, we have, in principle, two objectives with this work. The first one in what sense do granular matter and dense suspension flow differ? The second one is to develop an understanding of reality beyond the Einstein bachelor formulation, which is valid for dilute suspensions. But here we're going to try to develop a reality for dense suspensions instead. So the two systems we're going to study are these two. We have the systems which is consisted of hardware or grains, and we will share them in a planar shear cell. This is done at 0 temperature, so there's no Brownian motion. So the first case is where we have grains here, and we do a shearing under confined pressure. So we shear with a certain shear velocity, u, and the system has a finite size, which is h. So this has been previously been studied both experimentally and by numerics and also theory. So by some reference here, this is some of the references. It's not complete, of course. But what we are now interested in is to see the analog with a suspension case. So we take a system which is exactly as before, but now we take the grains and immerse them in a fluid with a certain viscosity eta. Shear rate in this case is simply defined as the difference velocities between the two walls, which we have two velocities, divided by the height of the system. So we start with a dimensional analysis of this problem. So we have, in principle, in the dry case, the granular without the fluid, we have two different timescales. We have the macroscopic timescale, which is just determined by 1 over the shear rate of the system. Internally in this ensemble of grains, we also have a microscopic timescale, which is the first one here, which is just the timescale for a grain to relax upon the pressure, applied pressure. So if we take the ratio between these two, we form a number I, which we here call the inertial number. And just from a dimensional analysis, we will find that mu, which is the shear stress divided by the pressure, is a sole function of this I, this dimensionless number. The same goes for the volume fraction, phi here, which is just defined as the volume of B divided by the total volume of the system. And as previously been shown in a numerics, several numerics papers, but also experiment, what we find is that the effective viscosity, first of all, it varies like the shear rate linearly, but we also find that it diverges around the critical volume fraction to the power of -2. So just to get the feeling what this inertial number actually is, or what kind of state it corresponds to. So here is a plot or a sketch I borrowed from, I don't know which publication it is now, but I stole this. So if I is almost 0, this means that we have a static heap of grains. If we take this heap of grains and we tilt the plane a bit, it starts to flow like a liquid. And this usually corresponds to inertial number between 0.01 and 0.1. If we tilt it even further, this means that we will have a lot of collisions and we will form a granular gas in principle. So the dry case has been calibrated. Here I show results from simulations, but you can also do similar in real experiments, and you get, in principle, the same result. So what people find is that, first of all, this flows the delayed. So while you shear, it will expand. And this has a very simple relation. It's even linear in I, to a good approximation, as you can see here. We also see that this is a yield stress fluid. So you need to have a certain stress before it starts to flow. When it starts to flow, again, it shows a linear dependence on I. So in the case of a suspension, we have one more time scale here. We have one more ingredients. We have the viscosity of the background fluid. By that, we can form a new dimensionless number. So we keep the old dimensionless number I, but we now also form a dimensional number J. And this is just a comparison between a microscopic timescale and eta f divided by the confining pressure. And this is a time for grain to relax upon a confining pressure when it's immersed in viscous fluid. By that, we will find that we will now have two new relations. We will have the friction as a function of both I and J. And the same goes for volume fraction, will also be a sole function of I and J, so a bit more complicated this time. And our question is now, how does this viscosity look like for dense suspension? What is the scaling both in volume fraction and in shear rate? So first, just some background. Of course, this suspension case is an old business. Einstein started to work with this, for example, 100 years ago or a bit more, where he found that at least in the dilute regime you can do expansion, and this is how the viscosity varies as a function of volume fraction. And in this case, the increase of the viscosity of a suspension is due to hydrodynamic interactions. However, we will focus on the dense system instead, where the volume fraction is very high. This means that most of the hydrodynamics can be ignored. Most of the stress contribution is coming from collisions and contacts and other things. There have been studies of this systems before. I show you here some result. However, this has usually been a semi-empirical approach. So here I show some data points which approaching a high volume fraction. But this is shown for a fixed shear rate. However, recent experiments have actually been focusing on this. So here is a clever setup, how to measure the viscosity of a dense suspension. You put the grains in a remeter. You have a confining pressure, but only for the grains. You have pores in your system, so fluid can go in and out. If you do so in a very viscous suspension, and if it's extremely viscous, what you can do is you can in principle ignore the inertial number I, because you can say that inertial effects will be subdominant. And the hypothesis is now that if you do so under confining pressure, it's like taking the dry granular case, taking I but replacing it with J. So we will see how this works. So this is the experimental finding of the suspension. And voila, this works excellent. So here you have friction as a function of J, the viscous number. You also have volume fraction as a function of J. Everything's collapsed nicely when you plot it as a function of J. You see also that this suspension, this dense suspension, is also a yield stress fluid. There is slight differences. For example, the scaling on volume fraction looks a bit different. Phi critical minus phi scales like J to the square root of J, while in the dry case, it's linear in I. So now to our contribution. So we do numerics of this. So we do discrete element simulations. We describe the grains particle explicitly. The fluid we describe in a continuum because it makes it simpler and faster. We then couple the fluid and grains through a two-phase model. The grain model, we use a normal grain model. So we have elastic forces when they overlap. We have a viscous damping. On top of that, we also have friction between the grains. So this is what people usually use when you simulate a dry granular system. On top of this, what we introduce now is also viscous forces. So here, so it's Stokes' drag in principle. The fluid profile, velocity profile, we solve by a feedback loop. So we get a steady state of the suspension. And when we do get a steady state, we start to sample all quantities we're interested in. So now to the question, how do suspension flows differ from granular flows? Well, here is some results, and here I represent my data as with a rescale pressure, I over J, which is just this number. So it tells me if I'm in the dry case or if I'm in the viscous case. So I over J, if it's low, means we're very viscous fluid. I over J, we're in the granular, so the background fluid is more or less air. So we see that by changing here, we plot here friction against volume fraction. By changing 5 decades of I over J, the rescale pressure, we see no difference. So it seems like a granular flow and a suspension flow is the same. Well, it looks like same if we plot friction against volume fraction, but what actually happens is that we change the time scale. The microscale time scale has of course changed, as we discussed before. But we can also see this in the dissipation. So if we measure where is all the energy dissipated in this system, we will see going from a viscous to a granular that the dissipation mechanism changes. We start, for example, on the green, everything is almost half is dissipated through viscous drag. And then we also have some contribution from lubrication. But the important thing is when we increase I over J, we see that everything goes to a collision dissipation instead. So again, we see that the latency increased very well with the previous experiment. As we share more and more, we see that the system delayed. This is true both in the viscous case and in the inertia case. So here we show two different plots. So here we try to collapse our volume fraction against I squared. Doing so, we see three of the curves collapse very nicely. All of these three corresponds to the inertia case. While we instead plot this as a function of J, we see that the three other curves collapse, while the three others which were collapsed before don't collapse anymore. We can do the same for the friction. Again, we see this is a yield stress fluid, as in the experiment. But again, if we plot this as a function of I squared, we see that some of the curves collapse, while we plot this as a function of J, we see that some others collapse. So the natural trick now is, of course, try to combine these two. So we form a new dimensionless number, K, which is just J plus prefactor I squared. By doing so, we managed to collapse all the data, so friction against K and phi against K. And this is, we also have some solid lines here, and this is just some fits we were able to do. By these fits, what we actually have done is we just said, well, the stresses, they come from two different kind of contributions. It comes from viscosity, the viscous term, but it also comes from the inertia term. We say that the dependence on the volume fraction from the viscous stresses and the inertia stresses are the same. If we do so, we can easily go through the equations, and we find that, voila, easily it drops out a dimensionless number K. So where do we actually have this crossover from viscous to inertial flow then? So if we look at this, the K number is just a function of two parameters, J and I squared. So if we take the ratio between these, we can easily identify this as the Stokes number. And we see also from the equations that if Stokes number is less than 1 over alpha, we're going to have stresses which is proportional to gamma dot. While if Stokes is greater than 1 over alpha, we will have stresses which is proportional to shear rating squared. So the viscosity, at least as a function of volume fraction for a dry and a viscous suspension, has the same behavior. And in this case, like phi critical minus phi to the power of 2. Minus 2, sorry. And this is also what found in the experiment. So after this, of course, ongoing, we have some other studies. We're about to study heterogeneous flow, and Mehdi Bouzid will discuss a bit about this later on. It would also be interesting to study turbulence in this dense suspension. So far, we haven't mentioned anything about this. And also to see what is the difference between a non-Brownian and a Brownian suspension. So what happens when we add a bit of temperature, and what is the relation between a jamming and a glass transition. And in that sense, we will have another dimensionless number, which is the well-known Peclet number. And by that, I want to thank you for listening, and also acknowledge some persons which I've been working with at USPC. It's Bruno, Philippe, Eric, Roche, and Mehdi. Thank you for listening.
Charlie?
You didn't go into any details about how you did the continuum fluid model. I picked up you've got a drag term in there, and then you have some lubrication term when the particles get close. Are there any other fluid-particle interactions?
No. So we tried, we did it very simple. We did first the simulation just with the Stokes drag, ignoring lubrication. But then we thought, well, I mean, there is some other hydrodynamic interactions which is important as well. Especially in this very dense suspension, we expect, for example, lubrication to be maybe dominate contribution to the stresses. So what we did, we added this as well, and in principle, what we got the same result. So what is only changed was this alpha, the prefactor between J and I. So it changed where the transition occurs a bit.
Could you see phenomenon such as pore pressure build up with the model?
So in the model right now, we lack this. So pore pressure, this is nothing we have in our model. Of course, it's very interesting to include this, for example, in connection also to turbulence, to see how the fluid actually...
I was thinking of liquefaction problems, but anyway.
Okay.
There's a good discussion to come there. Yeah.
Okay. In the Stokes drag, the fluid velocity is just a simply shear velocity, or do you compute the fluctuations around the?
No, so I mean, there's no fluctuations around it. We just we take a steady, we sample it in our two-phase feedback model. We sample profile of the fluid, and then we log this profile of the fluid. And we don't allow for fluctuations.
There's no entrainment of the fluid either.
No.
Yeah.
Yes, so in the inertial case, it seemed that you reminded us that the relationship between packing fraction and inertial number seems to be linear.
Yeah.
But I think there are data by Roux in the frictionless case that suggest that it's more power 1/2 there.
Yeah.
While for the viscous case, it doesn't seem to change, right?
That's true.
So maybe this mapping does not work asymptotically in the frictionless. Right?
Yeah. So I mean, what I showed here was only for the frictional case. It's true that if we do a frictionless case, it differs a bit in the dry case. So we haven't looked into this too deep, how this would change the collapse in this case. But it's a very interesting thing when we should do it. Yeah.
Mainly a comment. Could you go back to the drag law that you have been using? I want to ask you about the dependence that you use on the volume fraction, because there are some late studies, I think it's from 2012, I fail to recall exactly now the number, I can tell you, that show that for dense granular media, the drag law behaves like the law that you have for the viscosity. So it's inversely proportional to phi critical minus phi with the same exponent. So when you go to the phi critical, the volume fraction critical, then you have a divergence and you go to jamming.
Yeah.
So I don't know if you've used such a law in your model, but I could advise it could give different results.
Yeah, it might. I mean, we modulated this a bit, so we took into account of the Archimedes forces, which will lead to that this viscous force actually changes in these dense suspensions, but it changes like 1 over 1 minus phi. So it's not, it's regular because we never go above 0.80. So
Yeah, you're far away from one anyhow.
So we find, so it should not diverge in our case.
So this one, okay.
So,
I think that's proportional.
but maybe this is what we get from Archimedes in simple argument. So.
Okay, well, that's all we've got time for now, but there's obviously a lot more people who want to ask questions, so I'm glad we've got lots of time for discussion. Thank you again.